Okay, so take a look at these pictures. What's wrong? All right, I know, right? It's obvious. A lot of things. First of all, the structure for OMG, that ribonucleotide that's on the board, which is actually 2R, 3R, 4R, 5R, 5,2-amino, 6-oxo, 1H purinyl, 3-hydroxy-4-methoxyoxylano, 2-methyl dihydrogen phosphate, is a nucleotide abbreviated OMG, so the OMG part is right, but the code, the equation is not written in mathematical terms, it's actually written in computer code, and there's about 20 different things wrong with the structure on the board, including the hydrogen to hydrogen double bond. There's carbons where there should be nitrogens, and there's hydrogens in the chain creating up to 5 bonds, which is amazing. And hey, I don't, well, no goggles. Two, I don't know how valuable it is to teach electrokinetic densification to 11-year-olds. But anyway, we were on the same page, right? We were thinking the same thing. All right, anyway, Chapter 2, SI units and problem solving. Okay, a lot of this is this and that is that, and then we're going to show you 2 techniques that you're allowed to use in your problems. One, formula-based technique, and the other one, dimensional analysis technique. Third technique, if you create your own technique to solve the problem, that's called an apology letter. So this is about the techniques. So for instance, on a free response question in FRQ, you would get 64% credit for getting the problem right and 36% credit for using the technique. So for some stubborn people who don't want to use the 2 techniques I'm going to show you, the maximum grade you can get is failing, 64%, because part of the chapter is for you to learn the technique. But more on that as I go along in these Chapter 2 videos. All right, let's see what they start out with. Some stuff about the System International. See what they have to say here. SI units derived from entities that are constant. They never change over time from place to place. Okay, SI stands for System International, and because it was constructed, first put together in France in 1860. And scientists got together and said, look, there are a lot of different measurement systems. We have to come up with a standardized system that allows us to share data from country to country and scientist to scientist, lab to lab. The goal of which is we are going to, first of all, create units that are easy to communicate, and then we are going to create units that are based on things that never change. For instance, Celsius is not the SI unit for temperature. Kelvin is. Celsius, and they even say when you read it, they say degrees Celsius. Degree means compared to something else. And that's okay, except for the fact that the Celsius and the Fahrenheit systems are based upon the freezing point of water, 0 degrees Celsius, and the boiling point of water, 100 degrees Celsius. But the problem with the boiling point of water is that's only at a certain pressure, and that air pressure changes based upon your elevation. So for instance, water in Denver, Colorado, 6,000 feet above sea level, doesn't boil at the same temperature of water at South Brunswick. Water in Denver, Colorado can boil as low as 92 degrees Celsius. So you can't create a system on things that are constantly changing. The foot, right? We all know the old medieval story that the unit for the foot was started based upon the foot length of the king. You know, if your king is changing, your foot is changing, and your system of measurement is changing. So they wanted to get rid of all that and create a system of entities, which means things we are going to measure, like distance and volume and time, based upon things that never change regardless of where you are in the universe. And then, of course, the second thing is we decided to use, I wasn't there, but I decided to use metrics because the metric system is a system based on tens, and it's easier to compute and easier to translate and communicate between countries. Sounds like a good essay question. Hint, hint. All right, there's 2 types of SI units. One is called a base unit. And a base unit, here's what your book says. Entity which involves on one type. I love autocorrect. Only one type of unit. And what they mean by that is it measures one thing. For instance, the meter measures distance. Centimeter measures distance. Kilometer measures distance. Picometer measures distance. A kilometer is not a mathematical manipulation of the meter other than we're taking 1,000 meters and putting them together. In that sense, it's a mathematical manipulation, but it doesn't create a new entity. It still measures distance. It's just a different way of describing that distance. So here's the SI units, and somebody somewhere thinks it's important that you know all these, so let me explain them to you. And there's a bunch of other SI base units as well. The SI base unit for mass is kilograms. Now be careful with this statement. I almost want to get rid of it because it confuses people. I wrote grams and milligrams for chem lab amounts. That doesn't mean that's the SI unit just for chem labs. It means that when we go into the chem lab, we're not going to pour out a kilogram of reactants. A kilogram is 2.2 pounds. I mean, you're talking about a brick about the size of your arm. We would need a beaker the size of your bathtub. We would need a rowboat oar to stir it with. So general amounts that you use in typical chemistry experiments are probably going to be in the range of milligrams to a few grams, even though the SI unit is actually kilograms. So on test, make sure you write kilogram. But when you go into the lab, if you weigh out 2.2 pounds of stuff, you're probably going to get an F. All right. Length is, we know, meters. Volume, actually technically it's decimeter cubed. Volume is length times width times height. And each of those lengths, if they were 1/10 of a meter, and you come out to 1,000 cubic centimeters, that's equal to 1 liter. We typically just say 1 liter. I mean, this is what you would buy if you were buying juice in the store. You wouldn't buy a decimeter cube. But technically, the liter is not a standard unit. In fact, I hate this slide because I should change it. It's not even a base unit. It's actually a derived unit because it's a mathematical manipulation of distance times distance times distance. We'll get to that in a second. Time is measured in seconds in the SI system. The counting amount for molecules and atoms, we're going to talk about in Chapter 8. It's something called the mole. And it is, if a dozen is 12, a mole is 602 sectrillion, so 6.02 times 10 to the 23rd items. That is a lot of items. You do not have to know that number. That's called the Avogadro constant, and we'll talk about it in Chapter 8.2. The candela. Light intensity is measured in candelas. Well, a candela is about the amount of light you would get for burning a candle for 1 second. So the French were very clever there. Another French scientist, Ampere. We talked about electrical potential being voltage. Electrical kinetic energy is called the ampere. And temperature is measured in kelvins. You have to know the abbreviations, and you have to know which unit of measurement matches which entity. Again, temperature in Kelvin, electric current in amps, that sort of thing. All right, what's the difference between a base unit and a derived unit? A derived unit is not only a mathematical manipulation of base units, but it creates a new entity. You're going to combine the units, but now they're going to measure something different than what the original units were. Let me explain. Millimeter, centimeter, not a derived unit, because the base unit is the meter, but meter measures distance. Yes, a millimeter is 1/1000th of a meter, but it still measures a distance. Centimeter still measures a distance. So even though, yes, there is a mathematical interpretation there, it's not a derived unit. There are a ton of different derived units. The one you're most familiar with on this list probably is the Newton. And the Newton is a kilogram meter per second squared. And kilogram measures mass, and meter measures distance, and seconds measures time. But when you put them all together, it measures force. So you're measuring a new entity out of it. All right. So that brings me to formula-based problem solving versus dimensional analysis. The two types of problem solving that we'll accept on a free response question. Now, if it's multiple choice, you can use whatever you want. Get to the answer as fast as you need to get to the answer. But on free response questions, we are not only grading you on the answer, but we're grading you on the logic, the documentation of the logic, which means using the correct format. So there are two formats. This is the formula-based model. So you have to follow these steps in order. 1, write a formula. 2, solve for a variable, But I'm going to put a little star next to this, that only if you have to. I mean, sometimes if you have the formula density and they give you mass divided by volume, you don't have to solve for anything. The formula is already mass divided by volume. Now, once you have solved for the variable, then you substitute in values, but those values also have a unit of measurement. And if they're talking about, oopsie poopsie, teachable moment, if they're talking about a certain chemical, it also has to have the chemical formula out of it. So number, unit, label, I always call it labeling the chemical. Number, unit, label. It has to have all three things in the substitution. And then number 4, when you get to your final answer, we also have to apply what's called significant figures to our answer. We have to have the correct amount of precision, which we're going to talk about in another video. So it has to have the correct number with sig figs, the unit, and the label. All right, so let's go back to this other thing here. Let's pick a thing. All right. Suppose we have voltage, and a voltage is a joule per coulomb. Let's do that. All right, so we know voltage is a joule per coulomb. Suppose they say we have 254,000 coulombs, and we're going to use a 9-volt battery. I want to know how many, if we pass 254,000 coulombs of electrical charge, I want to know how many joules of energy that a battery is going to produce. Okay, so we can use a formula-based problem-solving technique here. We're going to write the formula. Voltage equals joules divided by coulombs. Now they want us to solve for joules, so our second step is to do that. So that means that a joule is a coulomb volt. Now we're going to substitute in number and unit. We don't have a chemical label here, so we don't have to worry about it. 254,000 coulombs times 9 volts. And even though I should, oh, here we go, handy dandy calculator. I was going to say, even though I should be able to do that in my head, I'm going to use calculator anyway, because why should I make a silly mistake? I get 2,286,000. Now, technically with sig figs here, the 9 volts means to only use the first digit, so we would round this down to 2 million. But I'm going to be reasonable here. Since the other one has 3 digits, I'm going to write 3 digits, non-zero digits, that is. So 2,290,000 joules of energy would come from that battery. I like students to box their answer. It makes life a little bit easier for me. And the one thing I always tell students, that the people who follow the correct format and logic documentation do so because they know how to do the problem. They want to make sure the teacher can see that they know how to do the problem, so they keep everything neat and organized and box things. When you're sloppy and all over the place and refuse to document your logic, one of the things that I always tell other teachers, look, to me, that is a way of obscuring the answer. Students who aren't hiding, students don't want to hide the fact that they know something. If they're being obscure, they're trying to muddy the waters and hide the fact that they don't know it. So again, the technique is part of your answer. Now, the other technique that we will accept is something called dimensional analysis. Go back here. And we're going to talk a lot about this in the next video. We're going to talk about how to take a base unit and convert it to some sort of other version of that unit, like meters to kilometers, etc., and to do it in an organized mathematical way rather than just shifting the decimal place. And this is sometimes called factor analysis, this choice, this technique rather. So, and I write here, hey, look, I care about students, but you don't have a choice in the matter. You have to learn these techniques because we're grading you on it. And the process for conversion problems is that you always start with what they give you, and then you manipulate that by multiplying by a fraction. That fraction is called the conversion factor. And then you're going to make sure that when you set up the fraction that the units cancel out. And then ultimately, you're going to make sure that that conversion fraction is a true statement. And we're going to go over this in detail in the next video, but I'll show you how it works. All right, so suppose we were doing that last problem. We know we're dealing with Well, now let's change it a little bit. Let's do a different problem. Suppose we are dealing with an object that we know has a density of 8.62 grams per milliliter, and we have a mass for that object of 2.16 grams. And they want us to predict what will be the volume of that object. Okay, so the technique is start with what they give you. And in this case, we're literally starting with 2.16 grams of the material. So we're going to write that. And then you're going to multiply by a conversion factor. And when you set up that conversion factor, you're going to start by putting the unit you want to cancel out, your starting unit grams, in the denominator, and then convert to a unit that you want to, for your answer, like milliliters for volume. And then you say, well, what is the true relationship between those two things? Well, the true relationship of those two things is the density of that object. And the density is, for every 8.62 grams, we have 1 milliliter of the material. So we're going to substitute in those numbers. We're going to say for every 8.62 grams, we have 1 milliliter. Now we can solve the problem. Because grams cancel out, we're left with milliliters, which is the unit we wanted. So we can now do the mathematics here. 2.16 times 1 divided by 8.62, and we get 0.251 milliliters. 0.251 milliliters. Now, could we have done that conversion or formula-based? Absolutely. Let's do the same problem formula-based. We know that the density is mass divided by volume, right? And we know, let's abbreviate that, M divided by V. And let's solve for V. So if we solve for V, we get V is equal to mass divided by density. Right? Now we substitute in volume equals mass, 2.16 grams, density, 8.62 grams per milliliter. The grams cancel, we're left with milliliters, and we still get 0.251 milliliters. All right, so either way would work in this particular case. And what I want to train you to do is to start looking at mathematical relationships like density, where there's a numerator and there's a denominator, and recognizing that those things can be dimensional, used for dimensional analysis. Those things can be used as conversion factors for problem solving. Now you look at this and you say, well, wouldn't it be easier, Mr. Burnett, if we just did the algebra and used the formula? In this case, yeah, I think it probably would be. I mean, it's actually more physical work, but less mental stress if you haven't done the technique before. But once you learn the technique for conversion factors, you'll be able to take a 10-step problem and bam, 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 just put down the fractions and cancel out all the units and you're done, rather than going through 10 formulas and trying to do some of them parametrically, which means, doing the whole substituting into other formulas. Much better problem solving technique for chemistry, at least for chemistry. So we're going to try to emphasize that in the next video. All right, that's all I got for you.